Moonshot AI just released Kimi K2.6. Nvidia launched Ising, the world's first OpenAI model family built to help quantum computers actually become useful. And OpenAI just gave Codex the ability to watch your screen, recording what you are doing, turning it into memories, and using all of that as context the next time you ask it to do something. So let's talk about it. Let's start with Kimi K2.6 because this is the one that made developers stop scrolling and start reading very carefully. Moonshot AI, the Chinese lab behind the Kimi assistant, open sourced K2.6 this week under a modified MIT license, which means anyone can use it, run it, and build on top of it. And the crazy part is the size of what they built. This is a 1 trillion total parameter model. That sounds huge, but here's the thing. Only 32 billion parameters actually turn on for any given token. That's the magic of the mixture of experts design. The model has 384 experts total, but only 8 get picked per token, plus one shared expert that always stays on. So you get the knowledge of a massive trillion parameter model, but you only pay the compute cost of a 32 billion parameter model at runtime. That's why this thing can scale the way it does without needing a data center to itself. The long context support is also serious, 256,000 tokens standard, and the architecture is multimodal from the ground up, not bolted on. It has a 400 million parameter vision encoder called Moonshot built right into the base model. So this is not a text model that someone added image support to later. It was designed to handle both from the start. Now here is where it gets interesting, the benchmark numbers. On SWE-Bench Pro, which is the test that checks if a model can fix real GitHub issues in real professional software projects, K2.6 scores 58.6. For comparison, GPT-5.4 on its highest setting scores 57.7. Claude Opus 4.6 on max effort hits 53.4. Gemini 3.1 Pro with thinking enabled lands at 54.2, and the previous Kimi K2.5 was sitting at 50.7. So K2.6 just jumped to number 1 on that benchmark. On Live Code Bench version 6, it scores 89.6 versus Claude Opus 4.6 at 88.8. And on Humanity's last exam with tools enabled, which is widely considered one of the hardest knowledge benchmarks in existence, with the tools variant specifically testing how well a model can pull in and use external resources on its own, K2.6 scores 54.0, beating GPT 5.4 at 52.1. Claude Opus 4.6 at 53.0 and Gemini 3.1 Pro at 51.4. That's the leaderboard position for arguably the hardest combined knowledge plus tool benchmark right now. But honestly, the benchmark numbers are not even the most impressive part of this release. The real story is what Moonshot actually showed the model doing in the real world. The first case study is almost unbelievable. Moonshot gave K2.6 a task to download a small AI model, implement inference for it in a programming language called Z, which is very niche and rarely shows up in training data, and then optimize the performance. The result was a throughput jump from roughly 15 tokens per second up to around 193 tokens per second. That's overall 12x improvement, and it ended up about 20% faster than LM Studio on the same task. Zero human help the entire time. The second case study is even more wild. Moonshot pointed K2.6 at Exchange Core, which is an 8-year-old open source financial matching engine, the kind of system that handles high frequency trade matching. It ran for 13 hours, made over 1,000 tool calls, modified more than 4,000 lines of code, tried 12 different optimization strategies, and analyzed CPU flame graphs to find hidden problems. It then changed the thread setup from a 4ME plus 2 RE config to a 2ME plus 1 RE config. The result was a 185% jump in median throughput, going from 0.43 to 1.24 million trades per second, and a 133% jump in peak throughput, going from 1.23 to 2.86 million trades per second. That's an 8-year-old code base that a human team might spend months improving. K2.6 did it in 13 hours with no help. And then there is the agent swarm capability, which is where K2.6 really becomes something different from a regular model. The previous version, K2.5, could coordinate up to 100 sub-agents working together on a task across 1,500 states. K2.6 triples that. It now scales to 300 sub-agents running across 4,000 coordinated steps at the same time. Moonshot demonstrated this with one run where 100 agents took a single uploaded resume and matched it against 100 job listings in California, then produced 100 fully customized versions of the resume, one for each role, in a single automated run. Another run took an astrophysics research paper and turned it into a 40-page, 7,000 word academic paper with a structured dataset containing over 20,000 entries and 14 publication grade charts. And on Browse.com, in swarm mode specifically, K2.6 scores 86.3 versus K2.5 at 78.4. On Deep Search QA, it hits an F1 score of 92.5 compared to 78.6 for GPT-5.4. Now, in fairness, there are limits of knowing. The model is recommended to run on VLLM, SGLang, or K-transformers, and it requires a specific version of the transformers library. Running 300 sub-agents in parallel is not cheap, and Moonshot hasn't published the exact compute cost for the swarm deployments. The model also can't take new instructions mid-run once a long horizon task starts. You define the goal and then you wait. That's the trade-off you make for 13 hours of autonomous work. Now let's pivot to Nvidia Ising, which actually landed about a week earlier on 14th of April, but it's worth covering now because together these releases paint a really clear picture of where AI infrastructure is heading. Quantum computers have been the coming soon technology for about 20 years. The hardware keeps improving, the research keeps piling up, but the gap between a quantum processor in a lab and one that can do something actually useful in the real world has stayed stubbornly wide. The reason is simple. Quantum systems are fragile. Their basic computing unit, called a qubit, gets knocked out of the right state extremely easily by heat, vibration, and basically anything in the environment. Before you can run anything meaningfully, two things have to work really well. First, calibration, making sure all the hardware is tuned and running correctly. Second, error correction, catching and fixing mistakes as they happen in real time. Both of these have historically been slow, manual, and very hard to scale. NVIDIA's answer is called Ising, and it's the first OpenAI model family specifically built to automate both of these problems. It comes in two parts. The first is Ising calibration, which is a vision language model. So it uses the same type of architecture that powers multimodal AI today, and it watches the diagnostic readouts from quantum processors and automatically adjusts the system to keep it tuned. The key number here is the time reduction. Tasks that used to take days of manual calibration can now be done in hours. In quantum hardware development, that difference between days and hours is enormous because experiments can't move forward until calibration is done. The second part is Ising decoding, which comes in two versions of a 3D convolutional neural network, one optimized for speed, one optimized for accuracy. These run in real time to catch and fix quantum errors as they happen. The comparison to the current open source standard, a tool called pi matching, is striking. Ising decoding is up to 2.5 times faster and 3 times more accurate. That's not a small improvement. That's the difference between an error correction system that keeps up with real-time quantum operations and one that falls behind. Here is the part that surprised a lot of people when this launched: the adoption list. Ising calibration is already live at Atom Computing, Academia Sinica, AeroQ, Conductor Quantum, Fermi National Accelerator Laboratory, Harvard, Inflection, IonQ, IQM Quantum Computers, Lawrence Berkeley National Laboratory's Advanced Quantum Test Bed, QCTRL, and the UK National Physical Laboratory. Ising decoding is deployed at Cornell University, Eden Code, Inflection, IQM Quantum Computers, Quantum Elements, Sandia National Laboratories, SEEQC, UC San Diego, UC Santa Barbara, University of Chicago, University of Southern California, and Yenzi University. That's day one deployment across national labs top universities, and commercial quantum hardware companies all at once. Usually, a new release tool takes months or years to reach that kind of spread. Ising did it on launch day. The models live inside Nvidia's CUDA-Q platform, which is their system for building hybrid workflows that use both classical computers and quantum processors together. They also connect to the NVQ link hardware bridge that lets GPUs and quantum processors talk to each other fast enough for real-time error correction. The models are available on GitHub, Hugging Face, and build.nvidia.com, and they are designed to be fine-tuned for different quantum hardware systems through Nvidia NIM microservices. And then there is OpenAI's Codex Chronicle, which is the third announcement and maybe the most talked about one right now. Codex already works as a coding agent. You give it a task, it goes off and writes and tests code on its own. The problem was always context. Every time you start a new session, you had to re-explain what you are working on, which tools you use, what the project structure looks like. Chronicle is designed to fix that by watching your screen. Here is how it actually works. When you turn Chronicle on, it runs in the background and captures screenshots of your screen. AI agents process those screenshots into written summaries that get saved as markdown files on your computer. The recordings themselves are kept only temporarily. OpenAI says they delete automatically after 6 hours. The next time you ask Codex something, it pulls relevant memories from those summaries and uses them as background context. So it already knows what file you were looking at, what error you were debugging, and what tools you had open. The practical difference is real. Instead of typing, I'm working on a React project using TypeScript, I use PNPM, not NPM. My test runner is VTest, and I was in the middle of fixing an authentication issue. You just ask what you need to know, and Codex already has that picture. It learned it by watching your work. Now, in fairness, OpenAI is being pretty open about the risks here. They say Chronicle burns through rate limits fast because it's running background agents constantly. It also raises the risk of what's called prompt injection. If you visit a website that has hidden AI instructions in its text, those instructions could end up in your memories and trick Codex into doing something. The memory files are stored unencrypted on your device. And here is an important detail a lot of people missed. The screen captures do get sent to OpenAI servers for processing before the final text memories come back and are stored locally on your machine. OpenAI says the screenshots themselves are not kept on their servers after processing, but that round trip is real and worth being clear about. This is almost certainly one of the reasons Chronicle isn't available yet in the EU, UK, or Switzerland, where privacy rules are stricter. It's launching as an opt-in research preview only for ChatGPT Pro subscribers on Mac OS. You turn it on manually in settings under personalization, and you can pause it anytime through the menu bar. Useful for sensitive meetings or anything you don't want being recorded. The question I'm sitting with is this. If an open source model from Moonshot is already at the top of the hardest coding and knowledge benchmarks, what does that do to the pricing power of the closed labs over the next 6 months? Drop your thoughts below, make sure you are subscribed, hit the like button, and I will see you in the next one.